This is our physics lesson on momentum, and when Newton wrote his Newton's second law, he didn't write it as F is equal to ma, so the one that you know before that we looked at the formula F is equal to ma, Newton's second law. Instead of writing this formula, he wrote that the force times the time is equal to mass change of the velocity. You see, if I divide both sides by t, I get force is equal to mass change of the velocity over the time, which is acceleration. So he didn't see the formula this way as force is mass equal to times acceleration. He saw it different way. He actually said if you apply force over a certain amount of time on an object that has a mass, that object's velocity will change. So this part is called impulse, and it has a letter J measured in newtons times seconds, and it equals to, this part is called momentum, or change of the momentum, P, and it is measured in kilogram meters per second. So you could measure this one in either units, and you can measure this one in either units. So this is how he looked at it. I'm gonna add some links to this video, so which one you should watch before you start doing the practice questions. So I'm gonna solve a few practice questions for you to understand how to use the formulas. Here's the first example we will do. So a soccer player kicks a 0.1 kilogram ball with initially at rest. So the mass is given. At first I'm going to write down everything that is given. So the mass of the ball is given. And initially at rest, I know initial velocity is 0. So it moves with the velocity of 20 meters per second. So now I know the final velocity is 20 meters per second. And it's good to write the units. And what is the impulse the player imparts to the ball? So if I'm looking for the impulse, I'm going to write the formula right away. Force times the time is equal to mass times change of the velocity. So this is impulse, but there is no force or time is given. But what they give you is the mass times change of the velocity. So I can say the impulse is equal to, the mass is 0.1, final velocity, change means final minus initial, final velocity minus initial velocity. So that gives you 2 newtons seconds. For the second part, they say if the player's foot was in contact with the ball for 0.01 seconds, so now the time is given, so the time is 0.01 seconds. What was the force exerted on by the player's foot on the ball? So the force times the time, again the same formula, is equal to mass times change of the velocity. I just calculated that this part is equal to 2. So I'm looking for the force. If I divide by the time both sides, then I have 2 divided by 0.01 times the top and the bottom, the numerator and denominator, by 100. That gives you 200 newtons. Here's another example. A mass of 750 kilograms, so the mass is given, 750 kilogram, is traveling east at the speed of 10 meters per second. So initial velocity is 10 meters per second. The car hits the wall and rebounces, moving westward with a speed of 0.1 meters per second. Because it changes the direction, I have to specify it with a sign, and velocity has a direction. So if initial was positive direction, then the final is going to be negative direction in the opposite direction. So that is going to be negative 0.1 meter per second. When you solve all the problems with momentum, it is very important to pay attention in what direction objects were moving before and after, or what directions objects were moving before the collision. So if there is always opposite direction, then you have to choose one of the numbers to be positive, the other one is to be negative. I chose after to be negative. So now I have to find what the impulse is. So the impulse is force times the time. They don't give me the force or the time, so they give me the mass, which is 750, and change of the velocity. The final is 0.1 and initial is 10. I'm going to distribute this number. So I have 75 negative minus 7520. So it looks like it's going to be negative 7575 newtons seconds. So that would be the impulse. Here is a very interesting example that tells you how impulse is the same or doesn't change, or momentum stays the same, but the force does change. So you have a 2,000 kilogram car, so the mass is 2,000, and traveling 72 kilometers an hour. So let's convert kilometers an hour into meters per second. So it's 72, kilo means 1,000, and hour is 3,600 seconds. So I can divide by 100 top and bottom. So it looks like it's going to be 20 meters per second. So the velocity initial is 20 meters per second. And it can be stopped in, at first, I'm going to do it in different colors. At first in 20 seconds. Then in 4 seconds. And then in 0.2 seconds. So, and I'm going to calculate for every single one, different cases. What is the average force for every collision? So I have force times the time is equal to mass change of the velocity. The final velocity is 0, so I have force times the time is equal to the mass, and the final velocity is 0 minus initial velocity, which is 20, gives me negative 40,000 newtons seconds. So that is impulse. The impulse does not change, but the force that is acted during such collisions will change depending on the time. So if I choose the force for this time, 20 seconds, then I get the force equal to, divided by 20, gives me 2,000 newtons, negative stopping force. Let's do it in this color. It's a stopping force, so it is negative, right? So now if I choose for a different time, 4 seconds, and your impulse is still 40,000, then the force in this case is equal to negative 10,000 newtons. And then if I choose the force to be 0.2 seconds, the new time to be 0.2 seconds, and that is equals to negative 40,000. Then the force in this case is equal to 200,000 newtons. And you can see how the force is increased depending on what kind of collision you have. So what you want to do is, in this formula, if you can increase the time, so the bigger the time is, the smaller the force can be. The smaller the force can be. Otherwise, if you have smaller time, your force is large. If you have bigger time, your force is smaller. So you want to reduce the force during the collision by prolonging the time, how long it takes to change your velocity. Here's the next question. The driver of the compact car with a mass of 6,000 kilograms suddenly applies the brakes hard for 2 seconds. As a result, the average force of 10,000 Newton is exerted on the car to slow it. What is the change of the momentum? So again, I'm going to write the formula. The force times the time is equal to mass of change of the velocity. The force that was applied is 10,000 newtons. The time it took to apply the force, 2 seconds, and it was average force. Doesn't mean it was always the same force, but over the whole time it was average of 10,000 newtons. The mass of the car is 6,000 kilogram. And what is the change of the momentum? Oh, they don't ask you change of the velocity, so change of the momentum. So the momentum formula is the momentum part. So here is momentum. And so if the impulse was the letter J, then the momentum was the letter P. So it equals to change of the momentum. And so if I multiply those numbers, so I have 20,000, momentum is measured in kilogram meters per second. So that would be for A part. For B part, what is the change of the velocity? So now I can say that it is 10,000 newtons times 2 seconds. And instead of writing change of the momentum, I'm going to write the mass change of the velocity. And they asked me to find the change of the velocity. So I'm going to divide both sides by 1,000. And then both sides by 2. So what I have is 10 is equal to 3 change of the velocity. So your change of the velocity is equal to 10 over 3 meters per second, or 3.333 meters per second. Then for C part, what is the final velocity of the car if it was originally moving at 12 meters per second? So the change of the velocity is equal to the final velocity minus the initial velocity. So if the change is equal to 3.3 meters per second, and it is the braking force that was applied, I could write a negative right here. The force, I could write negative, and I would get the loss of the velocity right here, negative 3.3, equals to the final. So they asked me for the final velocity, and initial was 12 meters per second. So the final velocity, I lost 3.3 meters per second from 12 meters per second. So my final velocity is equal to 12 minus 3.3, and gives me 8.7 meters per second. Here is another interesting example that involves the graphs, and that can be in your finals. So it's always good looking at this question. So I have the mass of the bowling ball equals to 7 kilograms. So the mass is 7 kilograms. And it's initially moving at 2 meters per second. Now, from the graph, I see that the force of 5 newtons is going to be applied on the graph, on the ball, for 1 second, between 1 and 2. So from here, I can say that force times the time is equal to mass change of the velocity. The force that was applied of positive 5, time that it was applied for 1 second. The mass of the ball is 7 kilogram, and I'm going to find the change of the velocity. So from the first part, so I'm doing the A part, I see that the change of the velocity is equal to 5 over 7, which is 0.7 meters per second, 0.72 meters per second, somewhere there. And because it's a positive force applying on the ball, then the velocity of the ball is going to increase. And because its initial velocity is 2 meters per second, then I know the final velocity of the ball is going to be 2.7 meters per second. for the second part, for B, the force that was applied was negative 5 newtons. So now I'm going to use still the same formula, but instead of the force positive 5, I'm going to write negative 5. So the force is negative 5, the time is still 1 second, the mass is 7 kilograms, and I'm still looking for the change of the velocity. So in this case, change of the velocity is going to be negative 5 over 7, or negative 0.7 meters per second. So because the force is negative, or stopping force, not accelerating force, the final velocity is going to be, we're losing the change of the velocity from the initial velocity. So we get 2 minus 0.7, which gives us 1.3 meters per second. So we had initial velocity 2 meters per second. We lost 0.7 meters per second, so the final is 1.3 meters per second. Also, in momentum, it's all about collisions and impulse. So when the collisions happen, usually two objects involved in collision, at least two objects involved in a collision. So there is such thing as conservation of momentum. In energy, you know that there's kinetic energy, potential energy, there's conservation of energy. For collisions, there can be different types of the collisions. Here are the few possible types of collisions that you can have. One is perfectly inelastic collision. So if you see in this picture, this is what's happening before. Two objects approaching each other, two balls approaching each other, and after the collision, this is after the collision, they stick together. So if two objects stick together after the collision, so that their final velocities are the same, this is called perfectly inelastic collision. In perfect inelastic collision, momentum is always conserved, but the kinetic energy before and after is not equal to each other. So the kinetic energy of this one is 1/2 mass velocity of the first one squared. Kinetic energy of this one, 1/2 mass of the second one squared. So this is how much energy they have before the collision. But after the collision, they have the kinetic energy of 1/2 mass of the first, mass of the second, because they stuck together, and the velocity squared after. So these two numbers, the sum of kinetic energy before is never equal to the sum of the kinetic energy after for inelastic collision, because not all the energy that they had is going to go to the energy of the motion. Some of it is going to be due to deformation between them when they collide together and stick together, breaking the bonds of the molecules and so on. So the kinetic energy is not conserved, only the momentum is conserved for perfectly inelastic collision. And one of the ways to remember inelastic collision, in means one gets in to another, and perfectly inelastic when they stick together. Second type of the collision is elastic collision. In elastic collision, two objects bounce after the collision to that they move separately. So before the collision you have two objects, and after the collision you have two objects. So before you can have mass 1 moving with velocity 1, mass 2 moving with velocity 2, and then you can have mass 1 moving with a new velocity, and then mass 2 is moving with a new velocity. So in elastic collision, I almost think like elastic, you stretch it and it always goes back to the same, to where it used to be. So elastic collision, you have two objects, you have two objects, and in this case you have momentum and the kinetic energy both conserved. In inelastic collision, so here you had inelastic collision and perfectly inelastic collision, this is another inelastic collision. In perfectly inelastic collision, they stuck together. In inelastic collision, they don't stick together, but there's some deformation happen during the collision. So it could be an apple, and I do not know, maybe the air goes through the apple and continues moving. You still have two objects after the collision, but one of them is damaged, so the apple would be damaged. So it would be inelastic collision, even though one got into another. Well, always, every time it gets into another, whether they stick together or damage done, kinetic energy is not going to be conserved. But momentum is conserved for every single one of them. So the momentum is always conserved. And what means conserved? Let's look at the formulas to understand what means conserved. So when we say momentum is conserved, we mean that momentum before, here at this part, momentum before, initial momentum, is equal to the momentum after the collision. So if you had mass 1 when it's with its velocity, so mass 1 with its velocity, it has a momentum because momentum is mass times velocity. And then momentum of the second one before the collision, mass times velocity of the second one. And after the collision, I have mass times velocity of the first one and mass times velocity of the second one. But here you had initial with I velocity, and here you have the final with the F, with the final velocity. And this is when they have elastic collision, or it could be inelastic collision. But for perfect inelastic collision, the formula would look like this. You have mass of the first one, velocity of the first one initial, plus mass of the second one, velocity of the second initial. And afterwards, because they stick together, you have mass of the first one plus mass of the second one in their velocity final, because they stick together. So their momentum is the same for both of them because they're becoming like one single mass. Let's look at some examples to see how we apply this formula. So here is number 13. A cannon of mass, so the cannon is given mass of 1,000 kilogram. And the cannonball, let me do this one big mass, and the cannonball is little mass of 10 kilogram. At the velocity of, launches at the velocity of, so the velocity of the cannonball is equal to 100 meters per second. What's the speed, at what speed does the cannon recoil? So I have to think about before and after. So every time I have these type of collisions, or there is a collision that's happening, that's why one is moving in one direction, the other one is in the other direction. And after, I will always start with I will always start with this type of setting where I have before and after. So what I have before is mass 1 of the cannonball and the mass of the cannon. They are stuck together because the cannonball is inside of the cannon. Their velocity initial is 0. And afterwards, you have the mass of the cannon, and we're looking for this velocity plus the mass of the cannonball times its velocity after, which is given 10. So the velocity of the cannonball after. So the masses before is 1,010 kilogram, and the velocity before is 0. The mass after, I have 1,000 kilogram for the cannon and its velocity after the collision, and then the mass of the cannonball times its velocity. So it looks like this is 0, so I'm going to subtract 1,000 from both sides, equals to 1,000 times the velocity of the cannon. So the velocity of the cannon is going to be -1 meters per second. So after the cannon shoots the cannonball, it will move backward at 1 meter per second speed. Here's another example. Starting from rest, 2 skaters push off against each other on smooth level ice. The friction is neglectable. The mother's mass, so the mass of the mother is given 100 kilogram, and the mass of the child, I'm gonna call boy, is 50 kilogram. If the mother moves away at the velocity, so the mother's velocity, well, let's call it, this is little m, mom, m for mom. at 2.5 meters per second, what is the velocity of the buoy? So the velocity of the buoy we're looking for after they push each other. So the before and after, again, before and after. So the before, I have the mass of the mom. So momentum before has to be equal to momentum after. So I have mass of the mom, velocity of the mom before, plus mass of the son, or the boy, velocity of the boy before, is equal to mass of the mom, velocity of the mom after, plus mass of the boy, the velocity of the boy after. So that's the velocity I'm looking for. So it looks like I have a 0 and 250 on the other side, plus 50 velocity of the buoy. So the velocity of the buoy is going to be equal to negative 250 divided by 50, which is negative 5 meters per second. So negative comes because it moves in the opposite direction from mom. Here I found another interesting example that I want to show you. So we have before and after. So the two blocks, one block is 4 kilogram, the other one is 2 kilogram. One is moving at 15 meters per second to the right, the other one at 3 meters per second to the left. And then they stick together and they want to find their velocity after. So I'm going to do the momentum before. The momentum before is mass times its velocity, plus the momentum before of the second one, mass times its velocity. Here, every time you see moving in the opposite direction, make sure you plug in a negative number for the velocity because they're not moving in the same direction. And then they stick together, so it's perfectly inelastic collision. Their masses together give you 6 kilogram because they're stuck together. And I'm looking for their velocity after. So it looks like this one is 60, negative 6, and here I have 6v. So this 54 is equal to 6v. So the velocity of both of them after are is going to be 9 meters per second. So I solved for you a few questions from our online lessons, and I want you to look at more questions. The answers are online, so for your own good practice, you want to solve as many questions as you can and see if you do understand how to use them, and if you see the tricks in those questions. The more you solve, the better you will do on the testing, and the better you show how much you understand everything you learn. Also, some videos attached to this video for the description, so watch those videos because that will help you. They will help you to understand the conceptual part of the subject. And thank you for watching it. See you guys later.